Hi, my name is Michael Ostroff, and I'm a PhD physics student at FAU. I am also a member of FAU's MPCR lab, and around last year, I was having a conversation with one of the professors in my lab, a philosophy professor by the name of Dr. Snyder. So she was wondering about we were talking about the Fermi paradox together, and she was wondering if perhaps aliens could potentially be utilizing extra-dimensional spaces in some capacity. And I was thinking about that for a while. Like, the idea stuck with me, because in order for that to be possible and aliens to be utilizing higher dimensional spaces, maybe 5 or 7 dimensional spaces or whatnot. We didn't go into numbers, but in order for them to be doing that, those higher dimensional spaces, or spacetimes, they would have to be coexisting with our current lower dimensional spacetime, over where we are. And I was trying to figure out how that could possibly work in theory, and that's when I realized something. You know what wormholes like to do in general relativity? They like to collapse in on themselves. Imagine you're in a wormhole, and somebody throws a bunch of matter into its throat or something, and now it starts going and collapsing in on itself. So what happens is you have this throat space-time, which is essentially these real extended dimensions producted with a compact space. And if you were to have something like a 2 torus compact, if the cross-sectional topology of the wormhole was something like a 2 torus, then if you were to be over here, you could go off the edge over here and wrap back around over here, and same if you were to go up here and you'd come wrap around like this. And if the wormhole was collapsing in on itself, this 2 torus, it would start to shrink and get smaller and smaller and smaller and smaller and smaller until it's astronomically small. And in general relativity, there's this thing called the Ricci tensor. The Ricci tensor tells you how dust clouds essentially change in hypervolume as they move along geodesics. And in a vacuum where the Ricci tensor vanishes, i.e. it's all zeros, a dust cloud, it should not change in hypervolume. Its hypervolume should essentially stay constant over its time evolution. So if you were to have a dust cloud in this collapsing wormhole, then as the cross-sectional topology shrinks and collapses in on itself, the perpendicular extended dimensions, the time dimension and the longitudinal dimension of the wormhole's throat, those both need to expand and in order to make the dust cloud's hypervolume constant. And essentially, when this occurs, the wormhole's throat becomes extremely long and extremely narrow. And eventually, the wormhole's cross-sectional topology, it becomes so small that it's essentially astronomically small. It's practically infinitesimal, but not quite infinitesimal. And when this happens, you can say that the cross-sectional topology of the wormhole has collapsed, and now it's a compact space you might find in something called Kaluza-Klein theory. So, I mean, compact spaces don't have to be microscopic and astronomically small, but in Kaluza-Klein theory, you're kind of assuming that they are. And these when you have this, so I should go into the history of Kaluza-Klein theory real quick, or not history, just going into how it works. So in Kaluza-Klein theory, there's this a 5D version of it, which is the original, where you have our normal 4D Minkowski spacetime, and you product that with a 1 sphere, which is essentially a manifold, which is a circle. If you just go around it, you come back to your starting point. Essentially, it's and the idea is that with one of these, which is really small, astronomically small, as projected was like our Minkowski spacetime, and this gives rise to a gauge field via the Kaluza-Klein mechanism, which in this gauge field is going to be like the U1 like field, which is like electromagnetism. And essentially, like via like this Kaluza-Klein mechanism, you can get like these sorts of like gauge fields from just like higher dimensional vacuum GR. Anyways, when you have a wormhole and it collapses in on itself, it should start to gain like these gauge fields via this Kaluza-Klein mechanism, depending on like the topology of the compact space, and it's like killing vector fields. And once this collapse has occurred, the dimensionality of the wormhole sprout is reduced by the dimensionality of the wormhole's cross-sectional topology. In the case of that 2 torus, that is a reduction by like 2 spatial dimensions, and you were left with a essentially a 1 + 1 dimensional space-time with a well, it's technically 2 like new like electromagnetic fields in the case of like a 2 torus. But if you were to have like the cross-sectional topology be a 2 sphere instead, which is just like the surface of like a ball essentially, then that would result in the creation of a SU2 gauge field, which is also an SO3 gauge field, which is essentially the group of rotations of like an object in like 3-dimensional space. Anyways, this made me realize that the dimensionality in general relativity, it's not exactly a fixed like thing. You could have a extremely high dimensional space-time and have like a wormhole like in it, and that wormhole could then go into collapse, and upon that like collapse occurring, you now have a lower dimensional space-time with like some Kaluza-Klein gauge fields present. So I'm calling these like weird structures which are able to change the dimensionality of space-time itself. I'm calling them dimensional collapsars because, well, they collapse dimensions. And I noticed something like a year ago, after I like came back from the Wolfram like summer school. I realized that an interesting like feature of these like dimensional collapsars, when they're like collapsing, I'm expecting it to be like this like violent and extreme collapse, and because like the collapse of this wormhole or dimensional collapsar, it fuels the expansion of the extended dimensions. This looks very, very, very similar, or at least it sounds very, very similar to inflation. And that is like this theory that in like the very early moments of our universe, it underwent like drastic expansion before like it slowed down a lot for whatever reason. So when you have this wormhole which is collapsing in on itself, this like either maybe it's like a 2-sphere wormhole or it's a 2 torus wormhole, whatever it is. When it's done collapsing, you go from the wormhole sprouts like space-time essentially goes from a 3+1 dimensional space-time to a 1+1 dimensional space-time with a 2-dimensional like compact space. So this is actually, I think it's the formation of a new lower dimensional universe essentially, and that the collapse of this wormhole is essentially the equivalent of its Big Bang. And for our universe, we know that in its like very early moments, it underwent like astronomical expansion, which then like slowed down for whatever reason. And this like theory, it's commonly referred to as inflation. I suspect our universe is itself a dimensional collapsar, and when it was forming, or maybe when like some chunk of space-time got sucked into our dimensional collapsar's mouth, that caused it to like violently like collapse essentially in like the extreme manner which like we would refer to as inflation, because like the compact space, like whatever it is for our universe, I'm guessing it's probably a like 1 sphere. because it collapsed so drastically, the extended dimensions expanded very drastically and inflated. So yeah. So this essentially tells me that dimensionality and general relativity, we normally think about it as this like fixed number where if you like look anywhere in like GR, it's like n-dimensional, and like if you look everywhere else, it's still going to be n-dimensional. But it seems that like general relativity should have this like property where the topology of space-time is able to change from like various different points. So you could have a region which is like Minkowski for like 30 like dimensional, like in like a 30-dimensional space-time over here with some like compact spaces, and then in that 30-dimensional space-time a dimensional collapsar forms, like essentially there's a wormhole, then it collapses in on itself, and then you have a lower dimensional universe which is created from that dimensional collapse, and it has like some more additional gauge fields. And oh, by the way, in Kaluza-Klein theory, the largest gauge field has the strongest coupling with the effective stress energy tensor. So if you were I'm guessing that the topology of like the compact space of like okay, so the cross-sectional topology of the wormhole, I'm guessing whatever it is, that becomes a new dominant gauge field in the universe which gets created. And whatever was previously the dominant gauge field, I'm guessing it is like it's going to be astronomically smaller than the newly collapsed topology, such that you wouldn't really observe any other gauge fields aside from that new one. Anyways, so like you should probably only have like at most one dominant gauge field in every universe. Anyways, so this like 30-dimensional like universe essentially gives rise to a bunch of lower dimensional universes by having dimensional collapsars pop into existence inside of it. And these lower dimensional universes, they're still going to be like high dimensional, and so dimensional collapsars start forming in them as well, and you get like more and more universes of like who have like different topologies essentially, or dominant gauge fields, and more dimensional collapsars keep forming in those until eventually you get down to like 4 dimensions, like where we are, plus like a bunch of other compact spaces. So I'm thinking that this is like a general property of like high dimensional GR. It's sort of like this there's this notion of like the curse and like blessings of like dimensionality and like data science, where like if you like or in other like complex systems where like the properties, they sort of change as you move into like extremely high dimensional spaces. I'm thinking that GR has like these properties as well, and higher dimensional spacetimes naturally give rise to lower dimensional spacetimes, so we get down to our level. And this begs the question, what is the actual dimensionality of this reality? Because with that 30-dimensional example, you could say that the dimensionality of that entire space-time is technically like 30-dimensional, even if like for places like here, it like most of those dimensions would be inconsequentially like microscopic compact spaces, which don't really influence our universe's dynamics. The universe, like, it likes either very small numbers or extremely large numbers like infinity. And if you are going to add, like, 4 is like a decent number of dimensions. It's not like too high, but if you keep adding dimensions, it starts to go from that like fine range of low numbers into an awkward range of like maybe like 10 dimensions or like 24 dimensions. And that's one of the reasons that people don't really like string theory. They feel it has like a lot of dimensions, but it's not high enough that it's like becomes more natural again. And I'm thinking that the most natural dimensionality for general relativity, like with all this in mind, is probably infinite dimensional, because if you had an infinite dimensional space-time, like an infinite dimensional manifold, it should naturally give rise to like dimensional collapsars, which give rise to universes of all sorts of dimensionalities, like all the way down, and like of all sorts of gauge fields. So any like sufficiently high dimensional reality should be able to give rise to like many different universes which have properties similar to ours in terms of being four-dimensional and having a dominant one-sphere compact space. So I've like, after like realizing all this like a year ago or so, I created a like new theory which I refer to as like Dimensional Collapsar Theory. It's sort of, okay, it is basically Kaluza-Klein theory, but like Kaluza-Klein theory is also general relativity, it's just like vacuum GR, but it's just like drawing attention to like compact spaces. It's basically like general relativity, but explicitly with compact spaces. So this Dimensional Collapsar theory of mine, it's essentially like just like vacuum GR and like Kaluza-Klein theory, but explicitly with dimensional collapsars as well. So it's not like it's as much of a like I'd say it's as much of a theory as like Kaluza-Klein is, I suppose. And I guess I'll leave that aspect there. So like this like dimensional collapsar theory, it essentially predicts like this like infinite dimensional like multiverse, and it's not like a many worlds interpretation multiverse, because like each of these like universes, they exist in the same like mathematical reality. You could, in theory, if you had some like warp drive, like travel outside the mouth of your dimensional collapsar and visit another dimensional collapsar and maybe like poke things in it with a stick or something, I don't know. And like these other universes which you could travel to, like I said, they can have different dimensionalities and dominant gauge fields, and they're not going to be like a mirror copy of our own universe. Like they're going to be a completely other universe. Or like you could go a couple of like universes over, and you're not going to find like a another version of yourself. It's just going to be completely unique, essentially. So, like, this is like the kind of multiverse that general relativity predicts, and like I don't think people haven't like looked into like wormholes like collapsing before, it seems, because this seems like, I think this like should have been like noticed sooner. Not entirely sure how this was missed per se. Another aspect of this dimensional collapsar theory, you remember when I was talking about inflation and how if the compact space were to shrink, the extended dimensions would have to expand? I'm thinking that this inflation, it might not have actually ended, and it might still be going on, but it just slowed down a lot, because if this if this compact space, like this S1 in our case, were to shrink a bit, then that would cause our extended dimensions to expand a bit. And this would look a lot like what dark energy looks like to us. And if you were to look at the, if you were to go to the Wikipedia page for Kaluza-Klein theory, and you were to like scroll all the way down to the part where it's talking about the like Ricci tensor and stuff like that, you would notice that there's a component, like a contribution to the effective stress energy tensor, which looks a lot like the contribution that dark energy makes, essentially. And this is essentially, this contribution is made by the dilaton field, which is like another name for the size of the compact space shrinking essentially over time. This would have the same effect as like dark energy, essentially. And I'm thinking that there might be another like potential effect here. I'm thinking that the size of the compact space might set the size of like particles, such as like Kaluza-Klein solitons, and if the like compact space were to shrink, then so would the size of particles. They would shrink in both like the extent of space and time. Like, it's just a hunch of mine. I haven't conclusively proved this yet, but working towards that. And if that were the case, then that would essentially exacerbate that the effects of shrinking compact space, because now like the particles themselves are actually smaller. So if this like dimensional collapsar theory of mine is true, then it should at least have predictions on how dark energy should behave, which could govern like the which actually should cover the time evolution of our universe. So we might be able to find observables regarding this, but I'm not entirely sure what the predictions are at this point. So I think that like wraps it up for today. I would suggest that you take a look at my Substack, which is Perpetual Science, and the same by the same name. I also have a channel on YouTube which I post videos onto, not currently very frequently. It's just some fractal related videos so far, but like I'm planning on putting more stuff on there eventually, and I should hopefully like have more stuff on my Substack like soonish or laterish. I should probably put stuff up about like wormholes and dimensional collapsar theory as well. That's a very important one. So I think that's it for today. Have a great day.